Laplace Transforms, Translation Theorems. If everybody is good, then we go. We're missing a lot of people, but unfortunately, we must teach. What are we calling translation theorems in this setup? Can everybody see this?
Yeah, I can see that.
Yes.
Thank you. So we start by what we call first translation theorem. And this has to do with the Laplace transform of a function that is multiplied by the exponential. First translation theorem. And then it says, if the Laplace transform of f of t is equal to capital F of s, then Laplace transform of f of t times e to the at is equal to capital F of s minus a. This is what we call the first translation theorem. So if we have the Laplace transform of a function as f of s, if I want to find the Laplace transform of that same function multiplied by e to the at, all I have to do is replace s by s minus a in the Laplace transform of the original function. This is also written as f of s, and then replace s by s minus a. It can also be written as f of t times e to the at is inverse Laplace transform of f of s minus a. Which means what? Written in this form, it means that if I have a function and I am thinking that this function is a translation, then I need to find the function that turns into capital F of s, multiply the inverse of that function by e to the at. How do I do this? I do this by removing from here, replacing s minus a by s to obtain f of s, and then go from f of s back to find little f of t, and then multiply by e to the at to find the inverse Laplace transform. So this is this second way you use that, right? To find the inverse Laplace transform. So we use it forward to find the Laplace transform of f of t e to the at as f of s minus a, and we use it backwards to find the inverse Laplace transform of a function when we suspect that there is translation. So we create that translation by replacing s minus a by s to have f of x. Then we find the inverse Laplace transform of f of s, and then we multiply by e to the at, the a being the one we got here, to get our answer. Am I making sense with this? So this applies in two different problems, forward and backwards. Examples. So one, and say Laplace transform of cosine at e to the kt, for example, we could say it's going to be Laplace transform of cosine at, and then we will replace s by s minus k, right? For the translation we have here. And then we are going to find Laplace transform of cosine at. What is it? Anyone to help?
Isn't it s over s squared plus a squared?
That's it. And this says replace s by s minus k. So you go into that formula and you replace s by s minus k. So that becomes s minus k over s minus k squared plus a squared. So this is the Laplace transform of cosine at e to the kt using the first translation theorem. Any question? An example 2, Laplace transform of t to the power n e to the at. What would this be? It is Laplace transform of t to the power n, then replace s by s minus a. What's the Laplace transform of t to the n?
Isn't it n factorial over s to the n plus 1?
That's correct. And then you're gonna replace s by s minus a. So that gives you factorial n over s minus a to the n plus 1. That's it. Pretty straightforward when you're applying the formula to find the Laplace transform of a function times e to the at. And it's only easy if you know the Laplace transforms. If you don't know them, it just look to you as Chinese to me. Now you do example 3. What's the Laplace transform of sine hyperbolic of kt e to the at? Have something to say, John? That was the first step here.
I actually didn't watch the last class, so I'm not 100% sure.
The first step is just this class. It has nothing to do with the last class. James?
You would do Laplace transform of sine of h of kt, and then to the s, and then change the s to s minus a.
That's it. And then what is this one?
Isn't it a over s squared plus a squared?
This is k here.
Then it would be k. Would it be k over s squared plus k squared?
And sine hyperbolic. So
I don't have the hyperbolic.
it is there. The only difference between the two is a minus.
Okay. Yeah, it's s squared minus k squared.
That's right. And now you replace s by s minus a. So you obtain k over s minus a squared minus k squared. That's it. That's how it works. Thank you. Now let's go with Messi, this one. So how would we get Laplace transform of sine at e to the kt? Devin? What's the first step?
The first step is it's the Laplace transform of sine at and replace s by s minus k.
That's correct. And what's the Laplace transform of sine at?
It should be a over s squared plus a squared.
Perfect. And then you replace s by
S minus k.
So you get a over s minus k squared plus a squared. All right, that's how it works. Any questions? This is forward. Now I'm going to give you questions backwards, how we work it backwards. The way I explained here. Is there any question on this one? All right, if there's no question, let's walk it backwards now. That's the best one. You're happy when you do it and you see the beautiful answer coming out. So now the question would be find the inverse. Laplace transform of, and then I go a s squared over s squared. This is not x squared, sorry, s over s squared plus 2s plus 2. And I ask you to find the inverse Laplace transform of that. And so you could say, okay, this thing is equal. And the first step is to identify the s minus a, okay? Because this thing here is f of s minus a. So this thing, you start by saying it is f of s minus a. You got to figure out what a is for the translation. And the best way to do that in this case is to look at that denominator, see if you can factor out things, because you know the standard Laplace transforms that exist. It's s over s squared plus a squared, s over s squared minus a squared. So you're thinking of that. That's why you think of the denominator, how you can work this thing out. And so if that was something with s minus a, what would be a? Here we would say that we will take s squared plus 2s minus 2 and plus 2 and say this is s plus 1 squared plus 1. And therefore, this is probably where we have our minus s minus a. So here, you're going to get s minus a is that s plus 1, so a is negative 1. Does that make sense? Please, if there is a problem, let us fix it right now, because this is the right time to understand. Does this make sense? So we factor out this thing, combine, we call it actually complete the square. We complete the square, and then we say, okay, that thing that is inside there, s plus a, the s plus 1 is the s minus a that we're looking for, and therefore the a is minus 1. And so in this formula, I'm going to replace s by s plus, you see here, I'm going to replace s minus a by s, which means I'm going to replace s by s plus a. So the first thing would be replace s minus a by s, which means s by s plus a. So this thing here is going to be replace s by s plus a. A is minus 1, so s minus 1 over s minus 1 squared plus 2 times s minus 1 plus 2. That is going to be f of s. If this is f of s minus a, then this is f of s by replacing s by s plus a in the formula after finding a. So the first step is you find that a. Second step, you replace s by s plus a in the formula to get f of s. And this is s minus 1 over this whole thing. When you open the parentheses, I believe is going to end up s squared plus 1. That's what you get. And so from this, you get a next step, you're going to find f of t, which is f minus 1. So it's inverse Laplace transform of s minus 1 over s squared plus 1. So the inverse Laplace transform of what you found in the first step. That's what I was showing here, that you replace s minus a by s, and then you find capital F of s. From capital F of s, you find little f of t. That's the step where we are now. We find a little f of t, and then we multiply by e to the at. So here, we do what we did last time. Now, our last lecture was about this, how to find the inverse Laplace transform. So this is s over s squared plus 1 minus the Laplace transform of 1 over s squared plus 1. And that is, this is cosine t minus that one is sine t. And then you go to the last step, you're finding your answer as f of t. So this is f of t. And your final answer is f of t is f of t times e to the at. F of t is cosine t minus sine t. And e to the at, a is minus 1, that's e to minus t. So this is your final answer to the problem. Any questions? Does anyone have a question? Nope. Let's do another one. Inverse Laplace transform of s over s minus 1 squared. So again, on this one, when you look at this, you see again, you look at that denominator, you see again s minus 1 squared, and you know that the powers, the Laplace transforms that you know are about just powers of n, like n factorial over s to the n plus 1. So you think of using the translation theorem here and have s minus a, in this case is s minus 1, so a is 1, because that's the whole thing that you have there that is squared. Now, if that's the case, you go to the second step, and then you do the f of s thing, replacing s by s plus a. S plus a is 1, so we replace s by s plus a, that's s plus 1. We replace s by s plus 1, becomes s squared here. So what we get is 1 over s plus 1 over s squared. This is what we get as capital F of s. So now we're going to find little f of t as inverse Laplace transform of 1 over s plus 1 over s squared. And this is 1 plus t. And so your last step is e to the at times f of t equals 1 plus t e to the t. That's it. Perfect, beautiful, short, and nice. Questions? Now let me give you this example that I hope you will easily do. Find the inverse Laplace transform of s minus 2 over s minus 5 squared minus 4. Use the translation theorem. This is s minus 5. Please let me know what you come up with. All right, who's trying? In step 1 here, what do we have? Or is S minus A here? Ethan? Is he here? Ethan? Michael?
I'm not entirely sure how to solve it.
Go and say something, Mason.
Is it S minus 5?
Yeah. So A is 5.
And you replace the S's with S plus 5s.
All right. So you get f of S equal S plus 5 minus 2. So that's S plus 3 over S squared minus 4. And then you're going to find little f of t. And this is S over S squared minus 4 plus 3 times 1 over S squared minus 4. This first thing is, and then this is inverse Laplace transform. Inverse Laplace transform. This is cosine hyperbolic of 2t plus 3/2 sine hyperbolic of 2t. Then you go to your last step. You can get f of t e to the ag. That is cosine hyperbolic 2t plus 3/2 sine hyperbolic of 2t times e to the 5t. That's it. So that's what the first translation theorem is about. That's how it's used. Now we can talk about the second translation theorem. Now let's see what the second translation theorem is about. And the second translation theorem is about the step functions. We used them earlier when we started defining the Laplace transforms. So step function is u of t that is equal to 0 when t is less than 0, equal to 1 when t is larger than or equal to 0. So this function is just as follows. The graph of the function cross goes through 1 fixed for any t, and then before that the function is right on the axis. So it's 0 up to 0, and then from there equal to 1 for everything. And one obvious thing is Laplace transform of u of t is Laplace transform of 1, which is 1 over s. Now, the function u of t minus a is obtained by translating the function u of t to start at the point A. So you have an A here, and the function is 0 all the way up to A, and starting from the point A, it's equal to 1 everywhere, up, going up. This is a translation of the function u of t. You translate it by just pushing it to the, you push it to the right. Push to the right, all the way to the point A. That's when A is positive, right? If A is negative, then you're pushing it to the left. And so the translation theorem states that Laplace transform of f of t minus a, u of t minus a, is e to minus as times the Laplace transform of f of t. So if I want to find the Laplace transform of the translated function, I just need to multiply the Laplace transform of the original function by e to the negative as. Using it forward is simple. You need to see that you have f of t minus a and u of t minus a. Using it backwards as well is simple. You need to see that you have the Laplace transform of a function times e to negative as. Then the inverse Laplace transform is equal to this. So inverse Laplace transform of e to negative as, Laplace transform of f of t, is f of t minus a, u of t minus a. So in order to use it in this form, you need to find f of t and then replace t by t minus a and multiply by u of t minus a. To use it forward, you need to make sure you see f of t minus a times u of t minus a before you write that. There's a little trick in that, okay? Examples. Let's say we want to find the Laplace transform of, let's say, cosine of t minus pi, u of t minus pi. Straightforward, it's written like that. F of t minus a, u of t minus a, that's standard form. So it's e to the negative pi s, then Laplace transform of cosine, which is s over s squared plus 1. That's it. Does this make sense? Are we still together, guys? There's something
Can I ask a question?
wrong about this class today. Everybody's so calm that I've never seen you guys like this. Yeah, miss.
Is the reason on the bottom is s squared plus 1 and not like s squared plus pi squared? Is that because the coefficient of t is 1?
Well, this is cosine of.
Because I know the cosine is s over s squared plus a squared.
So f of t here is cosine t. This is f of t minus a, minus a. The formula says f of t minus a, u of t minus a. So this is all t minus a. That's all t minus a. And so f of t is cosine t. And therefore, the coefficient is 1. Right?
I was just making sure. Thank you.
That's right. You got to ask like that. Otherwise, you're just wasting time. And it's very important to get that from here rather than later when you'll be on your own. So make sure you always see the t minus a first before you apply that formula. Let's get an example 2 where you need to do some work before you see that. Let's say I want to do I want to do Laplace transform of t squared u of t minus 2, for example. I want to find the Laplace transform of this, right? I want to see u of t minus a, and I want to see f of t minus a. Look at that. This is u of t minus a. So a here is 2, right? Because of the u you can see here, a is equal to 2. But question, do I see here f of t minus 2? No, I don't see that. I don't know what f of t is here. So what I do see here, according to the formula that is here, must be f of t minus 2. That's what I should be seeing. F of t minus 2 is t squared. Am I making sense? Because in the formula, you need to see f of t minus a times u of t minus a. So what I see here next to u of t minus 2 must be f of t minus 2. Now question, if f of t minus 2 is equal to t squared, what is f of t? That's the same thing we did in the previous thing with the first translation theorem. What do we do here to get f of t? Help.
Would it be t plus 2 squared?
T. So we replace t by t plus 2, right? So exactly the same thing we did on the other side. So here we replace t by t plus 2. That becomes t plus 2 squared. And now you can see that if I put in here t minus 2 to get f of t minus 2, that'll be t minus 2 plus 2. That's t squared. So I'm right. So that's correct. And that's how you find the f of t. And that f of t, you need a Laplace transform of it. So the answer here is equal to e to the minus 2s Laplace transform of f of t, which is t plus 2 squared, not t squared. And now you can go on to continue. E to the minus 2s Laplace transform. And the only way you can find the Laplace transform of this thing is to open the parenthesis, cross multiply. So that's t squared plus 4t plus 4. And then you find the Laplace transform of that, e to the minus 2s. Laplace transform of t squared, that is factorial n plus 1, factorial 3, that's 6. Factorial n, that's 2. Factorial n, 2 factorial, divided by s to the power n plus 1, which is 2 to the 2 plus 1 is 3, so that's s cubed, plus 4. Laplace transform of t is 1 over s squared, plus 4. Laplace transform of 1, that's 4 over s. That's it. And so this is how you will get the answer in this case. So most of the time, you need to do some work before you get the form to apply the second translation theorem. Any questions? Is there any question? All right, let me give you another example that you do by yourself now. And then we will do the inverse one. So find the Laplace transform of t e to the t u of t minus 3. I will give you 5 minutes for that. All right, who gives me the first step? Notice f of t minus a here. What is a, first of all?
3.
3.
A is 3, that's right. So, and what is f of t minus a, which is f of t minus 3? Hello?
Is it t e to the 2?
E to the t. Whatever else is in that formula is what f of t minus a is. And then if that is f of t minus 3, what is f of t? That's where we say replace t by t plus a.
Would it be t plus 3 times e to the t?
That's it. Once you replace that, you have f of t. And now you gotta find the inverse Laplace transform. And not the inverse, but the Laplace transform of f of t, which is Laplace transform of t plus 3 e to the t plus 3. Here you can come out with e to the 3 times Laplace transform of t e to the t plus 3 e to the t. And that's e to the 3 times, now you tell me, what is the Laplace transform of t e to the t? Laplace transform of t e to the t, please.
Would it be 1 over s minus 1 squared?
Yeah. And then Laplace transform of e to the t.
One over s minus 1.
That's it. So that's the Laplace transform of f of t. And the answer to this question is e to the minus 3s Laplace transform of f of t. And you got f of t, and you found Laplace transform of f of t, you need to multiply that by e to the minus 3s. So Laplace transform of t e to the t u of t minus 3 is equal to e to the minus 3s plus 3 times 1 over s minus 1 squared plus 3 over s minus 1. That's it. That's how you find a Laplace transform in this case. And notice that this example combines the two translations, because here what we did here is first translation theorem, and the whole thing was about second translation theorem. So this problem takes into account the two translation theorems. Questions? Is there any question on what we have done till now? All right, now let's do backwards what we have here. Find inverse Laplace transform of e to the 3s s over s squared minus 4. If I ask you to find the inverse Laplace transform of this, what would you do? First thing is, when you see a problem like this, you need to know that when you have exponential, that indicates there is a second translation theorem. And you know that in the formula of the second translation theorem, you have e to negative as Laplace transform of f of t. So whatever the exponential is showing is giving you a. In this problem then, in step 1, you have 3 is minus a. So a is minus 3. And you have Laplace transform of f of t, which is the second part of it, is the rest, whatever is next to the exponent. That is s over s squared minus 4. Now you find f of t. What is the function f of t that has Laplace transform s over s squared minus 4?
Isn't it hyperbolic cosine?
Okay, you're going to be tabling every.
So it's cosine hyperbolic of 2t. So that's f of t. And now, remember, in the formula, you have as well f of t minus a, u of t minus a on the left. So after finding f of t, we need to find f of t minus a. So f of t minus a here is f of t plus 3, which means replace in this formula t by t plus 3. So that's cosine hyperbolic of 2 times t plus 3. And so the answer is f of t plus 3, u of t plus 3. F of t plus 3, u of t plus 3, which is equal to cosine hyperbolic of 2 times t plus 3 times u of t plus 3. So that's the final answer to the problem. Again, the first step is identify a. You get a from the exponent. In this case, you got e to the 3s, which means negative a, because you have e to negative as. That means negative a is the 3 that you see. So a is minus 3. Now, whatever is left after the exponent is Laplace transform of f of t. So you write down Laplace transform of f of t equals that thing that is left. From this, you recover f of t directly. What is the function that turns into this Laplace transform? And that function is hyperbolic cosine of 2t. From this, remembering that the second translation theorem has f of t minus a, you find f of t minus a being negative 3, that is f of t plus 3. You know f of t, you replace t by t plus 3, you get hyperbolic cosine of 2 times t plus 3. And your last step is just to write the left-hand side of the second translation theorem, which states that f of t plus 3, u of t plus 3, is the inverse Laplace transform, which gives you this. Please ask me a question before I forget. Is everybody okay with this? Does it make sense? We are getting to the end of the course, so Very soon you will not have to see my face again. And maybe you will forget differential equations forever. Maybe you see them again in another class if you take courses like signal processing and others. All right. If there is no question, let me do another one. So, here I'm actually going to ask you a question. Why are we doing all this? Is this just for fun or just to make sure that your life gets miserable? Why all of a sudden in the differential equations course we are doing Laplace transforms, inverse Laplace transform, partial fractions, translation, all of that? What is it about? Is this just for fun? What does it have to do with the equations that we've been solving? Huh? No, believe me, I can guarantee it's not because I want you to be miserable. It does help solve certain types of equations. And what I want to do with the rest of the class time today is to give you an example of what all of this is about and why we are doing it. It's kind of jumping ahead to do the last section of this course in one example. Why do we do all this? All right. Assume we have an equation. Second derivative minus twice the derivative plus the function equals, let's say, e to the t. Let's say we have an equation like this, and y of 0 equals 0, y prime of 0 is also equal to 1. And so we want to solve this problem. Remember, when we used to solve problems like this, we have many steps. First step, solve the homogeneous equation, right? Second step, use variation of parameters or method of undetermined coefficients to find a particular solution. Third step, add the two solutions to see what you get as general solution. Then plug in the initial values to find the constants, right? How many steps are there? Many. At this point in this course, what we call the Laplace transforms here brings you a new method that does all of that in one step. So you don't need to solve the homogeneous problem. You don't need to find undetermined coefficients. You don't need to do variation of parameters. You just do the Laplace transform of that whole equation, and you find the Laplace transform of the answer. And then you go backwards to find the inverse Laplace transform of the Laplace transform of the answer to find the answer to the problem. And that's why we are doing Laplace transforms and inverse Laplace transform, because those are the two tools that you use to solve this equation. You use it forward to find the Laplace transform of the solution. Once you get it, you apply the inverse Laplace transform to get the solution. Okay. For that, let me say one thing here that we will see in the next lectures. I'm just giving you here to use it in this problem. We say that the Laplace transform of the derivative is s times the Laplace transform of the function minus the value of the function at 0. We will prove this. And the Laplace transform of the second derivative is the s squared Laplace transform of the function minus s y of 0 plus, no, sorry, minus y prime of 0. So these are the things that you have. So in this problem that we have here, we will say that the Laplace transform of the derivative is S Laplace transform of y, because y of 0 is 0. The Laplace transform of the second derivative is s squared Laplace transform of y minus 0 minus 1. And that's s squared Laplace transform of y minus 1. The right-hand side of the problem, Laplace transform of e to the t, what is it equal to? Everybody knows this by now. What's the Laplace transform of e to the t?
1 over s minus 1.
Great, 1 over s minus 1. That's what you get. And therefore, we take all of this into the equation. Laplace transform second derivative, that's it. S squared Laplace transform of y minus 1 minus 2 Laplace transform of the derivative, that's s Laplace transform of y, plus the Laplace transform of y equals 1 over s minus 1. Great. Now we solve this. This is s squared minus 2s plus 1 Laplace transform of y equals 1 plus 1 over s minus 1. Great. So you solve this and you get Laplace transform of y equals 1 over, and this is s minus 1 squared plus 1 over s minus 1 cubed. Guess what? This is the Laplace transform of the solution of the problem. We found it right away without doing anything. And so you can see that at this point in the solution, after 3 lines, we already use the initial values. We already, by the way, know what the solution of the homogeneous problem is going to be. And we, by the way, already know what the special solution is going to be. All of that in one. All right. And now all we need to do is find y of t as the inverse Laplace transform of what we got here. 1 over s minus 1 squared plus 1 over s minus 1 cubed. This is a beauty. You're going to tell me that. Now look, what's happening? What's the inverse Laplace transform of 1 over s minus 1 squared? This you know.
Is it t e to the t?
Great. That's the first translation theorem, t e to the t. Plus, and this one, translation theorem again.
Is it t squared e to the t?
Something is missing. You're almost there, almost. A number is missing. What's missing? What you do first of all, you got the e to the t. And so you can remove that from there. What you get is 1 over s cubed. What is this? What's the Laplace transform? The inverse Laplace transform of 1 over s cubed.
Is it times 2? Is
Yeah. I see that coming. It's 1/2, the number that is missing. T squared e to the t. So it's, and right there, that's the final answer. Final answer, including use the initial values. And look at that problem. We solve it right here. That's it. That's all of it. And remember how long we used to spend on this. And that's the power of the Laplace transforms, that they can allow you to solve such problems so quickly when the functions have Laplace transforms. On this, probably we stop today, and I hope I had enough advertisement for the Laplace transform that will allow you to go now home and do the homework problems. Thank you for today. I see you next time.
Thank you.
Thank you.
Thank you.
See ya.